Hello students, welcome to this lecture on the sequential circuits. So sequential circuits as such is very important for the subsystem design, for the VLSI subsystem design, in the sense that we normally have some component of the sequential circuits interface to the combinational circuit. So while we actually design the combinational circuit to to reduce the delay, to improve the power and then the footprint, the timing parameters is mostly dependent on the sequential design which we choose. So let's say that if we choose the latch design or a flip-flop design, so the combinational circuit has to be designed in such a way that it doesn't violate the setup and the whole time of the sequential circuit which is there in the subsequent stage. So in that sense, I think the sequential design is kind of very important for designing the overall subsystem, right? So for example, if I'm doing an adder circuit, the adder circuit's output has to go to the another combinational circuit, but it has to be timed. So in that sense, I'll have to introduce a flip-flop or a latch element in between the two combinational circuits. And while I'm designing the combinational circuit, or while I'm designing the adder circuit in this case, we have to ensure that it doesn't violate the subsequent the sequential the element such as the latch or a flip-flop which is there to interface to the other combinatorial circuit. So in generally in today's VLSI design or today's digital circuit VLSI design, we will see a lot of sequential elements just to time it out. To make sure that the combinational circuits output are well timed and it is kind of reached to the next combinatorial circuit in a proper synchronous timed manner. Alright, so in this particular lecture, what we are going to do is we'll try to understand the most primitive sequential element, and that too the latch design. We will try to understand how the latch design has evolved from the basic the CMOS circuits, right? So starting from the pass transistor, going to the transmission gate, and then some variant of the transmission gate, so that we will get a most robust the latch design, right? So moving ahead, as we understand from the latch definition, let me also pick up my pointer here. As we understand that the latch is a sequential element, and then by definition, what we really want is, for a latch design, and then this is a block diagram of a latch design, where I have the input D and then the output Q. So Q will be nothing but D in a transparent mode, and Q will be the Q previous in an opaque mode. So that's what I've written here, right? In a transparent state and then an opaque state. So actually the latch is defined in the transparent state. It's defined in two states. One is the transparent state and one is the opaque state. So the latch is actually working in two different states, transparent and opaque state. And during the transparent state, the output will follow the input. Whatever changes happens at the input, or whatever is the input level, we will get the output. And in an opaque state, at the output doesn't follow the input. So the output will be nothing but the previous output state, right? And this particular transparent state and opaque state are actually defined by the clock signal which is applied to the latch chip, right? So this is the very simple primitive definition of the latch. So the input and output are given with the clock. So if I have a clock in this particular, so this is basically the timing diagram of the latch design. So if I have a clock here, and for a latch, it is always defined by the clock levels. In this case, I've considered the high level of the clock, here. So only during this particular high level of the clock, the latch is in a transparent mode or in a transparent state. That means the output will follow whatever the changes happens in the input side, right? So and during this particular the negative clock cycle, it will be in opaque state, right? So that means that the output will not follow the input levels or the input changes, but it will retain the previous state, right? So here in this particular timing diagram, if the input is applied like this as shown in the D signal, and the output will follow the input during the high level of the clock, whatever is the input level, the output will follow Of course, there will be some kind of a delay. There will be some kind of a propagation delay. In this case, the output is rising. So it will be the propagation delay from D to Q, and it should be the rising one. And here the output, output will follow the input, of course, with some delay. And then this particular delay is defined as propagation delay D to Q, right? And it is falling, so it should be an F F labeling should be there. So TPDQ, which is nothing but the propagation delay from D to Q. Right, so this is how the timing diagram defines the latch. So most importantly, to summarize the latch design, what we really need to design for achieving the latch as a sequential element is there should be two modes, the transparent mode and then the opaque mode. Transparent mode, the output should follow the input, of course, with some delay. And during the opaque state, whenever the clock is at a low level, it should work like an opaque state where the output should not follow the input, and the output should retain the previous state. So with those definitions or with those specifications of designing the CMOS latch, let's try to understand whether the NMOS pass transistor, as a very simple primitive single transistor, can it work like a latch? So let's say this is the NMOS transistor with the gate. The gate is given to the clock. So the clock is applied to the gate. So if I have a VDD level and then a 0 level, VDD and then a 0 level applied to the clock, right, this particular level, we will have it as a transparent mode, and at this particular level, the low level of the clock, we will have it as a we'll have it as an opaque mode, right? So this will be opaque, and then this will be the transparent mode, right? So whenever the clock or especially the gate is applied with a VDD level, we will have it as a transparent mode, and then whenever the gate is is configured to the low level of the voltage, we will have it as an opaque state. Right. Now let's try to understand, during this particular two different voltage levels applied to the gate, whether it behaves like the latch. Right. Let's say this is the input, and the D signal is given here to one of the diffusions of the pass transistor, and what happens to the output. Right. So let me also draw the capacitance at the output side just to understand its effect. So the capacitor, let's say that initially it is not at all charged. So in initial charge is 0, and we apply a step input of 0 to VDD at this side. So the logic 1 is applied. So in that sense, this is anyways the gate, right? And then this is having a 0 voltage, so it will work like a source. It will act like a source drain, and then this one should act like a drain terminal, right? It is having a higher potential. So in that sense, VGS value is actually VDD minus 0, right? Initially, the capacitor is having a charge of 0. So we will have VGS as VDD. So it will have a channel here, right? So this particular channel, because this VDD minus 0 is greater than VT. So this particular channel will ensure that there is a charging path from the VDD to the capacitance. So a normal working of the pass transistor. Now this charges till it reaches VDD minus VT. Beyond that, this VGS value will be less than VT, and thereby this channel will not be there, and no more there will be a charging path. So the capacitor here, which is at the output node here, charges till VDD minus VT. So applying a logic level of 1 here at the output, I will get close to 1. Not really 1, but it will be 0.7 volts if I consider VDD as 1 volts and VT as 0.3 volts. Right, so a logic level of 1 is giving me a 0.7 volts here. And if I then change, apply the step input, make it back to 0 here, then this capacitor will have the charging path as a, as a normal pass transistor, NMOS pass transistor working. This capacitor will now actually discharge to 0. Right, so if I change this from 1 to 0 here, this will change from 0.7 to 0 volts. Right, whenever the gate is set at VDD. So it's transparent mode working of this particular the PMOS or the NMOS transistor, it is working perfectly well. Whenever the gate is at a high level, the output will follow the input. Especially when it is at 0 logic, we will getting the 0 logic here at the output, and whenever it is 1 logic, we will get 0.7 volts at the output. Now, if let's say that I have this transistor, the pass transistor, and let's say it is at VDD. I have applied 0 to VDD here, the step input. So the capacitor here will get charged to VDD, and after that the gate voltage is changed to 0 volts. That means now it is in an opaque mode. It should be in an opaque mode. That means that the output should not change, right? So when it does change to 0 here, the VGS value, right? The VGS value, in fact, the output will be VDD minus VT. So the VGS value will be minus of VDD minus VT. Suddenly, when as the clock is applied, when the gate voltage is sees a 0 volts here, it will be in a cutoff mode. This transistor will be in the cutoff mode, and whatever the channel it had been formed earlier to charge this particular output node, it will disappear, and the output voltage will be retained at VDD minus VT, because it doesn't have a discharging path, or it doesn't have a charging path anymore, because the gate voltage now sees the voltage of 0, and thereby it is in opaque mode. So this particular, a very simple pass transistor, an NMOS pass transistor, is behaving like a latch, right? Because it satisfies both the transparent mode operation as well as the opaque state operation, right? The NMOS pass transistor, it works like a latch, provided if the gate voltage is given the clock signal and the input is applied to one particular diffusion side, and the output should be taken from the other diffusion terminal. So in that sense, the NMOS pass transistor works like the latch, whatever we need. But there are some disadvantages, and let's have a look at the disadvantages. So the first disadvantage is output doesn't swing from rail to rail, right? So the output, whenever it reaches to 0 perfectly, because the NMOS pass transistor passes a successful 0. But when the input is at VDD, it actually reaches to 0.7 volts or VDD minus VT. So it doesn't pass a successful logic level 1. So it is passing a very weak logic level 1. So that is what is one of the disadvantages. It doesn't, the output doesn't swing from rail to rail. So it actually swings from ground to VDD minus VT. Alright, hope this is clear. The second disadvantage is, the output is dynamic. That means that, this particular output node, if I consider as a capacitor, it is, let's say it is charged to VDD minus VT. All right. And now the gate is, fed with a 0 volts. That means it should be in opaque mode. So it should be in a locking state. So the output, it reaches to VDD minus VT. And it is should retain at VDD minus VT, right? Let's say there are some changes at the input here. Input, from 1 it has gone to 0. Even if there is some change at the input side, in the opaque state, when the gate voltage or the clock voltage is 0 at a 0 level, we should not have any changes at the output, right? So let's say this is the input, and then this is the clock. Right, the clock is at 0, that means it's an opaque state, that means the output should be retained irrespective of the changes at the input. Right, so even if the input changes here, the output should not change, but rather what happens is, due to the subthreshold leakage current, right, which will be in terms of nanoamperes, right, the subthreshold leakage current, because the 0 volts applied at the gate side, falls into the subthreshold region that is below the VT, and we know that there will be some kind of a leakage current. There will be some kind of a leakage current that is possible from drain to source side. Although it will be nanoamperes, there will be a small amount of current that will be going back from drain to source. So there will be a drop in VDD minus VT voltage. There is a possibility of a drop of the voltage at VDD minus VT. Right, and we know that the subthreshold leakage current, which is defined by this particular expressions. So when VGS is, even if it is at VGS is 0 volts here, I have a VDS which is VDD minus VT, right? And even if we say that VSB, the source is at 0, the body is at 0, if this is 0 here, we will still get I of current and 10 raised to eta minus of Vt divided by S, and this eta is 0.1 and S is 0.1, so this gets cancelled, and then we will get close to 10 raised to minus 0.3 is 501 I of current. The I of current is generally around 5 nanoamperes, 5.63 nanoamperes for a NMOS transistor, and so we are likely to get somewhere around 2.51 nanoamperes, but still there will be a some amount of the leakage current, and if this opaque state remains for a longer duration, even the small subthreshold leakage current is likely to have a greater drop in the output voltage. So that is the problem. So I cannot actually have the opaque state for a longer duration, right? So that the output should be retained, but it doesn't get retained, and there will be a drop in the output voltage because of this subthreshold leakage current. And that is the reason why it is called as the dynamic, right? So the output is floating, so the output remains floating and can drop due to the subthreshold leakage current during the opaque state. The third disadvantage is it is actually sensitive to the noise on the input side. All right. So what it really means is, let's say that I have an NMOS transistor, and then we are using this NMOS transistor for the latch design. And let's say that these are the output states and the input states which it has been reached. So the output state it has been reached is VDD minus VT, and then the clock signal has gone to the 0 level. So that means that the latch should be in opaque state, right? So VDD minus VT should not change now, irrespective of the changes at the input side. Let's say the input has changed to 0. And we notice that, of course, there will be some kind of a leakage current, subthreshold leakage current, which will make this drop. But irrespective of the subthreshold leakage current, if let's say that at the input side there is a noise signal, which gets coupled to this input of the NMOS transistor, right? So this let me say that this is an input noise, and the input noise is of the level of minus Vt. Let's say that I have a mixed signal circuit, and then close to that, and the mixed signal circuit is then very close to the digital circuit, where the digital circuit has this latch design, and we have used the NMOS transistor for designing the latch. So in that case, I will have some kind of a coupling effect. The coupling effect is going to have a minus Vt voltage, this kind of a signal that will be coupled at the input of this latch, and then let's say this is the output. So a coupling, the noise coupling at the input here, D, right? And if it has a minus Vt here, or greater than minus Vt, then I have this VGS value going to be equal to or greater than Vt. So this particular voltage, VGS, will now be greater than or equal to Vt based on this noise signal. If it is minus Vt or more than, or more than minus Vt, in the sense the magnitude is more than the Vt value, then in that sense I have this VGS greater than or equal to Vt. So this particular transistor, although it was supposed to be in opaque, it will now be on. That means there is a channel that is being created here. The channel allows the further drop of the output voltage. So the output voltage is not retained to VDD minus VT anymore, and it gets dropped further. So that's why it is, it has been said that it is sensitive to the noise on the input side. The other disadvantage is it is sensitive to the noise on the output side as well. And the reason is very simple. If I have, it's in the transparent state, let's say that it has reached 0 and it has reached, the input was 0 and then the output was 0. And then the clock is at a higher level. So it is in a transparent mode. So whatever is the input here will go to the output here. But then at the, let's say that this particular, the output line of this particular latch is very close, closely coupled to any other circuit, and that particular circuit is having an input, having a noise that is being coupled at the output side. And let's say that the noise is characterized like a positive VT here. So this particular positive VT here, right, will have an effect on the change in the input side. So let's say that all these values are 0 and 0, but then there is a noise signal of VT here, right? And VGS is anyways VD, so there is always a channel that is being formed in the transparent mode, in the transparent state of the D-latch. This particular transparent, the channel here allows any kind of voltage that is being applied at the output side to be shared at the input side. So what happens is, if suppose a voltage of VT comes here, the VT here will get sufficiently discharged to the 0 value here, right? So the VT it will decrease to VT by 2 on this particular side, and then VT by 2 on this particular side, right? Assuming the capacitors on both the sides, then there will be a charge sharing effect from the output to the input. And then the charge sharing will have an immediate effect on the output levels. So instead of 0, it will now be considered as VT by 2 on the output side, and it will have an impact on the input side as well. So it is kind of sensitive to the noise on the output side as well. Right? Hope this is clear. So we had 4 disadvantages of using the NMOS transistor as a latch. Although the NMOS transistor can be utilized as a latch. So let's see what happens if I use a transmission gate. So if I have a transmission gate, that means that the NMOS and the PMOS transistors are tied together in parallel. So one thing is very clear, that the output swing is not restricted to VDD minus VT anymore. It gives the output swing from 0 to VDD, because either of the PMOS and the NMOS will ensure that will give a successful logic 1 and pass a successful logic 1, or pass a successful logic 0. So I'll get a rail to rail voltage is achieved. So that first disadvantage is kind of removed by using a transmission gate as a CMOS latch. The second one of the output being dynamic, and that is output being floating, and due to the subthreshold leakage current, it can actually get dropped. That still retains, especially during the opaque state, that is still remaining in the transmission gate, right? So the third and fourth, the sensitivity to the noise on the input side as well as on the output side, are also retained here in the transmission gates, and we can see one such example here. So in the last to last slide, especially when we talked about the NMOS transistor, here I'm going to talk about the PMOS transistor, how it is kind of how it is sensitive to the input noise. So let's say that the phi is 0, that means it is in opaque mode. So in a transmission gate, if the NMOS gate is 0, the PMOS gate will be nothing but the complement of 0, so it will be at logic level high, or the VDD voltage. And let's say that the output is now maintained at 0. So in the previous state, when it was in a transparent mode, the output is completely discharged to 0. So this particular logic level of 0 is been achieved in the previous transparent state. And let's say that now the input has changed, and changed to VDD here, and there is a noise signal that has been coupled at the input side, right? With a noise signal of VT and above VT, this VGS value will now be minus VT or lower than minus VT. Will make sure that the PMOS transistor will have a channel here, and with this particular channel we will have some kind of the charge sharing from the input to the output side, right? And that's the reason why the input the output is kind of very sensitive to the noise on the input side. So that is still remaining. The fourth disadvantage of sensitive to the noise on the output side, I'll take an example here again. So let's say that the phi is 1, so it is in a transparent mode, right? So whatever is the input, the output is going to get reflected, and because it's a transmission gate, phi bar will be 0 here. And let's say that it applies at the input side, it is 1 logic, and then the output has achieved a logic of 1. And at the output side, if it is coupled with a noise signal of Vt or less than Vt, then in that case there will be a drop at the input side. So this gets coupled into the input side, right? So the input voltage, if the other parts of the input voltage doesn't drive this particular node, then this particular node is now has a possibility of getting it decreased, right? So due to the charge sharing from the output to the input, the output, the changes or the noise at the output is going to have an effect on the input side, right? So in that sense, it is sensitive to the noise on the output side as well as the noise on the input side. And then the second disadvantage, which is still there in the transmission gate while we are using the transmission gate as the latch design, is due to the subthreshold leakage current, the output node is dynamic and it remains to be floating, and there could be a drop in the output voltage due to the subthreshold leakage current. Now, how do we solve this? We need to solve this so that we will get a very robust latch design. So let's say that can we use the inverted transmission gate or an inverted buffer design? So inverted buffer design means I will have an inverter first and then followed by the transmission gates. So the transmission gates with the clock at the gate side, so phi and phi bar given to the gate of the NMOS and PMOS transistor respectively, and the input is applied to the inverter. So I will actually get a complemented latch output. And let's say that for time being it is perfectly fine. I don't really care about getting a complemented or an uncomplemented logic. So if D is 1, the Q bar will give me 0, and if D is equal to 0, the Q bar will be 1 in a transparent mode, right? And by definition, the opaque mode, whenever the clock is at low level, the Q bar should be retained. Whatever was the Q bar in the previous high level of the clock, it should be retained. Because it's a transmission gate, we will, we know that the output will swing from rail to rail voltage 0 to VDD, right? So let's say that the output state doesn't change based on the input noise Vt running on 0. So this particular, the inverter will ensure that even if I have a noise signal here on the input side, as was there in the previous case, it is not going to affect the output of the inverter, right? And if it doesn't get affected at the X node, it will not have any effect on the Q bar signal or the Q bar output, which is nothing but the output of the CMOS latch. Right. So now let's try to see what the inverter, how the inverter makes that difference. Let's say that I have an inverter here at the input, and then this is the X. So this is the D signal and this is the X signal. The X will go to the transmission gate and then give the Q bar signal. Right. So as previously, if I have a minus Vt or below minus Vt here, right, previously because of this transmission gate, which was directly taken as the input, we used to get the NMOS transistor to be on because this was set to be 0, and in the opaque state, even in the opaque state, if the input noise was going below minus Vt, right, my VGS level was was greater than Vt, and then this particular NMOS transistor was turned on, and thereby the output might have a change based on the input signal. Right. So in this particular case, even if it reaches minus Vt, because of the inverter here, right, because of the inverter here, if I draw the inverter transistor, so VDD, and then I have a PMOS and then an NMOS, and then this is my output. So this is my input signal. Even if the signal goes below minus Vt here, the NMOS, right, is either of this. Now this was anyways on, and then this was off initially also, even when it was 0 volts, and then the output was anyways turned to 1, right? Even if it goes to minus Vt here, this will still remain off, right? Because my VGS value will be negative, not only 0, but it is now negative, and this negative value will not have any effect on the change in the operations of the NMOS, right? So the NMOS will still be off, and then there will be no change in the output, there will be no change in the X value, no change in the Q bar value. Similarly, as was previously seen, if I have a noise signal above the VDD, right, noise signal above the VDD, then in that case, it will not have any effect on the X output voltage. Because when it was at VDD, right? We will anyways have the PMOS to be off and then the NMOS to be on, and the output voltage will be pulled to 0. And a greater voltage than the VDD of VT with a value of VT, it will not have any effect, right? So the PMOS will still be off and then the NMOS will still be on, right? The noise signal on this particular inverter will have an effect only if I get, whatever is the input here, whether 0 or VDD, if it goes above VTH of the inverter, right? Whatever is if the inverter is a skewed inverter, if it's an unskewed inverter, we know that the threshold voltage of the inverter was around 0.5. So if the noise signal is above 0.5, the noise signal is below 0.5 for the VDD rail, or it is above VTH for the 0 voltage level, then only this X value will change, right? So any small level or a small low level noise signals will not have any effect on the inverter side, and that's the reason this inverter is going to avoid the small signal noise, right? Especially at the input side. So inverter is insensitive to the small input noise signal. It reaches, that because of the transmission gate, the output rail to rail swing is achieved. Insensitive to the noise on the input side because of this particular inverter. And output still is dynamic, floating, and it can drop due to the leakage current. All right. Now one can consider that we have an inverter here, and that is going to be driven by either the VDD rail or the ground rail. So this X is kind of a driven one. Now why will the output here of the transmission gate or the latch is going to have a drop or an effect? Because the X value is anyways driven by the rail voltages, right? The reason one such case I can give is, so let me pick a new slide. Okay, so what we have is the inverter followed by the transmission gate, right? And then this is my output signal. Let's say that the output signal in the previous clock cycle has reached 1. So this has to be 1 and this has to be 0, right? In the previous clock cycle, so this gate voltage was VDD or 1. And now it has gone to the opaque state of 0. And once it has reached the opaque state of 0, let's say that there is a change in the input from 0 to 1 and then it has reached to 0. Right, so if I draw this particular transistor level diagram for the inverter, so I will have a VDD here, I will have a ground here, right? So it is now 1 here, and that's why this particular, I'll call this as an X node, and then this is Q bar, and then this is D. So I will have a D signal as 1. The X signal is now completely discharged to 0. Right, and then we have this transmission gate. The transmission gate clock or the gate voltage is set to 0, and then phi bar will be nothing but 1. Then I will have this output of this latch or the transmission gate, which should be retained at the logic level of 1. But because this goes to 0, right, or rather this particular node voltage is actually driven by this NMOS transistor, which is on now, right? The subthreshold leakage, and if it is kept opaque, or if it is trying to retain the logic level 1 for a longer duration, right, the subthreshold leakage current, which will flow towards the ground, right, will slowly keep dropping this voltage values from VDD to a lower value, right? So even in an opaque state, because of this subthreshold leakage channel, there will be a change in there could be a change in the output voltage if it is maintained for a longer duration, right? Hope this is clear. So adding an inverter at the input, it makes it insensitive to the input noise signal. Similarly, if I have, this is another variant of the CMOS latch. So the earlier one was an inverter followed by the transmission gate. Here it is a transmission gate followed by the inverter, or a buffer followed by the inverter. So there is no inverter at the input side. The inverter is there at the output side. So what it does is the output Q bar is now, this particular signal is now isolated from the X. And what it does is, even if I have a noise signal here, if I have a noise coupled at the output signal, right, it will not have any effect on the X input. Now it's very simple, because if I consider the inverter, right, and then the output here and then the input here, right, any kind of the noise that has been coupled in the input will not have any effect on the input signal, right, because output signal is anyways driven by the VDD or by the ground, right. So any noise input signal here at the noise signal at the output side will not have any effect in the input side. So this inverter is making sure that the output noise signal is not captured into the latch design. And because it's a transmission gate is there, the output swings from rail to rail, and then the output is still, it is still dynamic. The reason is if this is kept for a long duration in the opaque state, there will be a drop due to the subthreshold leakage current, drop in the X node voltage, and will have an effect on the Q bar output signal. And lastly, it is still sensitive to the noise on the input signal, right? So if I have some kind of an input noise here, which can get reflected at the X node, right? Which can get reflected at the X node, and then this X node changes in the X node will have an effect on the Q bar signal.